Okay, so let's finish up our notes on section 4.1. Last week we introduced this topic of 2D equilibrium of a point. And we have these notes from last week where we kind of went through what we thought equilibrium should be. We practiced making a couple of free body diagrams. We went through some springs and some pulleys. Those are the special cases that we kind of need to know about when we're doing 2D equilibrium of a point. And then we went through a couple of examples. So the purpose of this video is to finish up the last couple of examples for this section. So we finished up during the last class with figuring out the weight of this girder, and now we're going to move on to this next example on page 5. So what we're given is a 2 kilogram block at point D is suspended from the two springs as shown. So if the block and springs are in equilibrium as shown, determine the original lengths of the two springs. So just right away we can look at this diagram and we can tell what our deformed lengths of our springs are as they sit, because they are in equilibrium now. So as always, let's do our first step, and let our first step be drawing a free body diagram. So let's make sure I've got all this set up correctly, and let's just do step 1 can be draw a free body diagram of the point. And kind of as you have seen, there's a theme to these problems. So the free body diagram of the point, we kind of want to pick the point where all the cables meet, right? So we're going to do point A. So we're going to draw a point. This is point A, and all of these will be in tension on point A. So we're going to draw these forces acting away from the point, and we'll call the upper right one FAB, call the upper left one FAC, and then finally the force that's acting down on point A is due to the weight of the block, which is 2 kilograms. So we will just call this weight is equal to 2 kgs times 9.81 meters per second squared, which is 19.62 newtons. And that is a complete free body diagram. We do know the angle of these forces. So this one is a 3-on-3 slope, which is just 45 degrees. And then this one is a 4 horizontal, 3 vertical slope for FAB. Okay, so we've drawn a complete free body diagram at point A. You know, there's 3 cables coming in at point A, so that means there's 3 tension forces applied at point A. So next we need to apply our equations of equilibrium, and let's do this maybe in blue. Okay, and let's just do it over here. We'll just do it right here. Let's apply our equations of equilibrium, EOE, to our free body diagram. So if we look at our free body diagram and we sum forces in the X, and as always, let's just assume to the right to be positive. If we do that, then we have a negative FAC sine 45 plus 4/5 of FAB, positive because it acts to the right. And then the weight force acting at point A has no X component, so those are the only two we have, and we set that equal to 0 because we're looking at a free body diagram that is in equilibrium. So repeating this step here for the y direction, we'll assume up to be positive. What we find is we have FAC positive. I'm sorry guys, I have these backwards right here. The x direction would be cosine 45, and then the y direction would be sine 45. FAB is also acting upward, so it's going to be positive. It will be positive 3/5 FAB. And then the weight force acts completely downward, so we have minus 19.62. It's in equilibrium. Set it equal to 0. So now what we have here is two equations, some forces x and some forces y, and two unknowns. We have FAC and FAB. So two equations, two unknowns. It is a solvable system of equations. And if we do this, just solve those two equations simultaneously by substitution, what we find is that FAC is 15.86 newtons and FAB comes out to be 14.01 newtons. So now what we just essentially have done now is figured out what the force is in each of these springs. So the problem wants us to determine the original lengths of the springs. The spring constant of each of them is given to us. KAC is 20 newtons per meter and KAB is 30 newtons per meter. And we know the final shape. So all we have to do is just back into what the original length was, given what the force in the spring is. So if we remember from our lecture last week, we derived the equation for the force that's in the spring is equal to F equals K times some delta L, right? Well, for what we're doing, we're trying to find delta L because we know K and we now know force, so we can calculate delta L. So let's do that. We'll change back to red so that it's a little easier to see. Step 3, delta L. So delta L of AC would be force in AC divided by K of AC. Which the force in AC was 15.86 newtons, and KAC is 20 newtons per meter. So our delta L comes out to be 0.793 meters. All right, repeating the same process for delta AB. It's just force AB divided by K of AB, and that is 14.01 newtons divided by 30 newtons per meter. And what we find is that the delta L of AB comes out to be 0.467 meters. So all we have to do to find the original lengths is take the final lengths and subtract out the delta L's. If we look at this, the final length of AC, we'll just write it here, is, you can do square root of 3 squared plus 3 squared. So length of AC in the final position is 3 times square root of 2, and length of AB in the final position is 5. Okay. that is the length of these springs in the final position. We know how much they have deflected from the original position. So all we do is take this, the final positions minus the deflections will give us the originals, and that's what we'll say is length AC original comes out to be 3.45 meters, and then length AB original comes out to be 4.533. So that is our answer for this problem. That was the original length of those springs. Okay. So since this is a video and you don't get to ask questions, let's just keep moving on to our next example then, where we look at another load, a crate that's supported at point A by a rope that goes up and over a pulley, and the pulley is suspended from a rope at point D. What the example wants us to figure out is determine the maximum weight of the crate and the angle theta if all of the ropes can only hold 100 pounds. So, first things first, as always, let's draw our free body diagram. So step one, free body diagram. I'm going to draw the free body diagram of point C. So this is point C. We're going to have some force acting straight down at point C from the weight of the crate. We're going to have a force acting down and to the left for the rope that goes from BC, and then we're going to have a force that goes up and to the right from CD. So we'll label those FCD. This will be FBC, and then this is FCA, but it just is equal to the weight weight of that crate, but we don't know it. So FCA. Our FBC force is a 5 horizontal, 12 vertical, and then we are trying to figure out the angle at which FCD needs to be applied. So let's just take a look at this free body diagram and notice that FCA is just going to be equal to the weight of the crate, right? So we'll just call FCA is equal to the weight. Through our special cases that we determined last week for our pulleys, any cable or rope or anything that goes over a pulley has got to have constant tension across the pulley. So instinctively we know that the FCA is equal to the weight, but knowing that the pulley has to have constant tension over, we then know that FBC must also be equal to the weight. All right. So moving on from here, let's go ahead and set up our equations of equilibrium and see what those give us. So again, let's sum forces in the x direction, let to the right be positive, and let's start with FBC, which is W. It will act to the left, so it is negative 5/13 W. The FCA is completely vertical, so no x component, and then we have FCD, which will have an x component. It acts to the right, so positive FCD, and then the x component will be cosine theta. And those are the only two forces that we have acting at point C in the x direction. It's in equilibrium, so we're going to set that equal to 0. Repeat the process for the y direction. Some forces in the y direction up to be positive. What we find is negative 12/13 W minus W plus FCD sine theta is equal to 0. Okay. So if we look at our sum forces in the y equation, and we know that FCD and FCA and FBC all can't exceed 100 pounds, what we can see is that FCD is going to be, if we're looking at the equations for the y, we have negative 1 and 12/13 W, and then sine theta FCD. Sine theta is always going to be less than 1, right? So we've got a very small FCD, which means FCD is going to reach 100 pounds first, okay? So let's just write that so that we can see this. Note that FCD will reach 100 pounds before W. Okay? So if FCD is limited to 100, then we're trying to find out the maximum weight that it can be carried. All we have to do then is set FCD equal to 100 and solve for W. So FCD, we'll set it equal to 100 pounds, and then just plug it back up into our equations. So what we get is W is equal to 13 over 5 times 100 cosine theta. This is coming from equation up here. If we know FCD is 100, that's 100 cosine theta. Move the negative 5/13 W to the right side of the equation. This is what we're getting. And so if we solve this equation we just wrote, that comes out to 260 cosine theta. And then plugging W into our sum forces in the y direction, what we get is negative 12/13 times W, which we just said was 260 cosine theta, plus 100 sine theta, minus W, which we said was 260 cosine theta. And all of that equation still has to equal 0. And what that comes down to be is 100 sine theta minus 500 cosine theta is equal to 0, which reduces down to tangent of theta equals 5. And what we find is theta is equal to 78.7 degrees. And when you plug that back into your weight equation, 260 cosine theta, we find that the weight comes out to be 51 pounds. And that's our answer. Okay? So what this is telling us is that if I have a crate that weighs 51 pounds, that will develop 100 pounds of tension in FCD. Okay? Now let's take a pretty kind of conceptual view of this. If AC is 50 pounds acting straight down at C, BC will also equal 50 pounds acting, mostly down, right? 12/13 down. So if I have 50 pounds down and nearly 50 pounds acting down from FBC, does that not kind of mean that FCD needs to be pretty much 100 pounds acting straight up? Which is what we find. We set FCD equal to 100 because that's the maximum it could be, and then our theta came out to be 78.7 degrees, which is quite steep. So it does make sense if we have right here 50 pounds acting down and then 50 pounds acting mostly down. It stands to reason just conceptually that this upward force needs to be right at 100, right? Which is what we figured it out, which is what we solved for. Okay? So it makes sense. So let's move on to the next problem. We've still got 2 problems left. And we'll start looking at this problem. So we've got this contraption here where we have a rope that goes over 2 pulleys attached to some springs, and the problem says the springs on the rope assembly are originally stretched 1 foot when theta is equal to 0. Now we want to determine the vertical force F that must be applied to point A so that theta will become 30 degrees. Okay? If the springs are already stretched 1 foot when theta is equal to 0, before F is applied, so this is all in its original position, but the springs are already stretched 1 foot from their unstretched position, what does that tell us about the tension in the rope before F is ever even applied? And what it means for us, and we're going to write it here, is that there was an initial tension in the ropes before F is ever applied. So we're going to just write this out. Notice there is initial tension on the ropes before F is applied. And we can go ahead and calculate what that initial tension was, right? So the force is equal to, the spring force is equal to F times delta L, right? The K for both of these springs up here is 30 pounds per foot. And then it is stretched 1 foot. So there is 30 pounds of tension already acting away from point A, going both left and right before F is applied when theta is equal to 0. Okay? So do we know the length of the original position, right? Do we know what BA was before the F was applied? That answer is yes. Okay. So let's go back here. What we need to do is start trying to figure out what the spring forces are after F is applied. Okay. So the original length, BA sub O, all right, BAO, was 2 feet. You know, it was this dimension right here. When theta is equal to 0 and A was up here, the length from B to A was 2 feet. Can we all agree with that? But now that F has been applied, the length of BA post displacement is now some other dimension. So let's just say BA in the deformed position, it comes out to be 2 over cosine of theta, but we want to know what F is when theta is equal to 30. So we'll say 2 over cosine of 30 to figure out what the length of BA is in the deformed position. And that comes out to be 2.3094 feet. Okay? So from this, we just deduced that the rope has to extend by 0.3094. All right, which means that's how much the spring has to extend as well. So the force in the spring then is F times K. F is equal to K times delta L. K is 30 pounds per foot. It stretched by 0.3094 feet. And we find that the force in the springs from F comes out to be 9.28 pounds. Okay, so that's the force in the springs. But there was already initial force. So we find that then the force in AB is also, it's all symmetric, right? Left and right. So we'll say FAB is equal to FAD, 30 plus 9.28, so 39.28 pounds. Okay. So we just solved what the forces are inside the ropes and the springs. And now we just need to apply our free body diagram and our equations of equilibrium. We'll look at a point. We'll look at point A there. All right, both of those are 39.28 pounds. Their angles are 30 degrees from the horizontal. Oh, that's not right at all. 30 degrees. And then we have the F force acting straight down. Basically, all we need to do is solve for F, so let's just solve for forces in the y direction up to be positive. And what we have is 39.28 times sine 30. And then we have it twice, right? We have for FAB and for FAD. So I'll just take this, multiply by 2. That's positive because they act up. Subtract F out for the force that acts downwards. It's all in equilibrium. So set it equal to 0. And what we find, you just solve that equation, is that F actually comes out to be 39.28 pounds because sine 30 is 1/2. Okay? All right. So let's do one more example then, and we will call it a wrap for 2D equilibrium of a point. So last example, what we have here is we've got this pulley assembly. The rope that goes from A, B, C, and D, rope A, B, C, D, is 4 feet long, and the block at point D weighs 10 pounds. What we need to do is determine the weight of the block at B if this assembly is in equilibrium in the position that we're given. Okay? So I want to know, determine the weight of the block B if the assembly is in equilibrium as shown. Easiest thing to do then would be to draw a free body diagram of point B. But there's a couple other things that we need to take notice of first. So we don't really know what these angles are. So I'll tell you what, let's just draw the free body diagram at point B first. Okay, so free body diagram, right here will be point B. We'll have some weight of the block, we'll call it WB, because weight of the block at point B. And then we're going to have forces FBC and FBA, FAB. Okay, but we don't know right off the bat the direction of FAB and FBC. We know that they act in these directions, but we don't know the angle or anything like that. So what if we do some geometry to figure out these angles? This dimension here has got to be 0.5 feet. This is 0.5 feet, and then this dimension has got to be 0.5 feet. But what about the hypotenuse AB, or the dimension from point B up to the horizontal here? How can we figure this out? And we have to kind of rely on our instincts here to know that the assembly is constructed with a 4 foot long rope. So 4 feet long is the total length from A, B, C, and D. So the way we can do this is length AB is equal to the length from B to C, which is equal to 4 feet minus 1.5 feet over 2, because we have 2 segments of it. And those come out to be 1¼ feet. And if we know that this is 1.25 feet, and we know that that's 0.5 feet, we'll call this angle theta here. And so what we find is that sine of theta is equal to 0.5 over 1.25, and that comes out then that theta is equal to 23.58 degrees in the equilibrium position. So if the theta is 23.5 degrees to the vertical, then these angles here will be 90 minus theta, which is 66.42 degrees. It's the same on both sides. And now we actually have something that we can start working with. And keep note too, since we're working with pulleys, if block D is 10 pounds, then the tension that is in this rope all across these pulleys is 10 pounds. So FBC is equal to 10 pounds. FAB is equal to 10 pounds. And now that we know both the magnitude and the direction of FAB and FBC, we can just solve for WB. So step number 2, let's apply our equations of equilibrium. We only need one since we're only got one variable in the y direction. So some forces in the y, assume up to be positive. What we have, it is symmetric again, so I'm going to just multiply by 2, and it is 10 pounds times sine of 66.42 minus WB is equal to 0. And if we run that equation out, WB comes out to be 18.33 pounds. So the weight of the block then at point B, if the block at point D is 10 pounds, the block at point B needs to weigh 18.33 pounds for the assembly to be in the shape, or in the to have the dimensions as they're shown here in the diagram. So that should be all that we cover for 2D equilibrium of a point. All right. The next couple of steps that we're going to be working with is to expand our equilibrium of a point by one more dimension. So we're going to do 3-dimension equilibrium of a point. That's section 4.2. After that, we will be moving on to 2D equilibrium of a rigid body, which is pretty much the same thing as this, but instead of it just being a point, we're going to be looking at any kind of rigid body, whether it's a beam or a column or a truss or whatever. But that will be after our 3D equilibrium of a point. So this will conclude our video on 2D equilibrium of a point.